All right, so this is 885, and it says Run Length Encoding. And it gives an example. So I'll click on the example tab over here. It says, this is an example of a lossless compression algorithm called Run Length Encoding. It defines what a run is right here. It says a run is a sequence of the same character repeated multiple times. So the example that I will give in this, I'll say something like, no way, and it has a bunch of like Y's at the end of it. And you can actually, we talked about a little bit about compression and then decompression, that you're able to compress things to ultimately be able to send smaller files or be able to work quicker. And there's different compression algorithms. And this is just one that they made up on the spot here. They've called it the Run Length Encoding. Maybe it's not made up, but they've made up the problem below that we'll end up going through. So a sequence of characters is repeated multiple times. An example here says like what with a bunch of A's after, or I guess not after it, but WH and then a bunch of A's. 1, 2, 3, 4, 5, 8 A's. Okay. It says this compression algorithm works as follows. I'm right here. It says compression takes all runs of characters and replaces them with the character written once, followed by the number of times it's repeated. So for example, if you were to take A, 6 A's, by using this run length encoding, we could turn those 6 characters into 2 by just writing A6. Okay, this is just a method of encoding. It's very easy to understand. It's not one that's used frequently, but we're using it as an intro to compression. It says the naive implementation of this algorithm converts single character runs to run length format as follows. It turns B into B1. Now, if you're turning one character into 2 characters, is that really compressing anything? No, it's adding to it. So with that, you would, in the example below here, it says what with 8 A's gets turned into W1, H1, A8, T1, and then question mark 1. And it only saved us 2 characters, right? So maybe a more valid way of compression would be like, maybe if there was only a single character here, maybe if it was just the W, just the H, that we wouldn't put a number after it. That might be the easier method of going about it. But this is just the way that they've come up with. It isn't very sophisticated, and that's why it's even called it naive, right? So I would say the word instead of naive that I would use is just say the unsophisticated method of this, right? It might work and you might understand it, but it also in many cases might not actually compress anything. It says, unfortunately, the naive implementation, it uses naive again, of this algorithm can actually cause the compressed string to be longer than the original, right? It would change what into this, and it actually doubled the number of characters. So they use the word naive. I would use the word unsophisticated, or inefficient, I guess is another good one. There are maybe better ways to do this. So it says this algorithm needs long runs of characters in order to be effective, right? I use the word ineffective. So in order to be effective, in order to compress something down, we would need like 25, not 25, but you need a really long string of characters in order for this to be successful. It says the algorithm only works when a value is repeated 9 or less times. Now, decompression. So if you compress something and then you decompress. Like you hear this used frequently, like you get home after a long day and maybe someone's on you. Like for me, like it might be like my kids. I might tell them, hey, I need time to decompress, right? The entire day you spend like, just like imagine like squeezing something and that tension and the stress, and then you get home and you need time to decompress. So the compression is making things smaller, and the decompression is restoring back to a state where people can talk to you, restoring back to like, hey, I feel better now after a long day. Maybe some of you understand that feeling. I don't feel it as much, but after a long day, after we put the kids to bed, I need time then to just like spend some me time. I'm more introverted, and that's how I function. So it says to decompress the compressed text, simply take each pair of character number and repeat the character that number of times. So W one time would be W, H one time, A 8 times, and so on. Okay. Now, if I didn't look over here, I would be doing myself a disservice. Okay. I need to be looking over here and reading through the code. If you're not reading through the code, even if you don't understand it, read through it, take your time, and try to trace through the code and see how it works. I need everyone's attention over here. Okay. It's on your screen, that's fine, but we shouldn't be typing or doing anything else. It says, this program is an example of simple lossless compression. Okay. It's going to be using a very similar method, or the same method that we just talked about, the run length encoding. Okay. So if we look at it, right, the first thing that I like to do when I see a program, right, if any of you guys ever bring your code up to me, first thing I do is I just go all the way to the end. I look through it a couple times and just see, without even reading through, see how long it is. I try to find how the program is structured, and I see that we've defined several functions. We've defined a function called compress, which takes an argument and received as a parameter called original. We also have another function called decompress, which takes an argument and it's received as a parameter called compressed text. And then down here is actually where the program begins. And I'm looking at this, and it prints out, well, first it asks a question. It says, enter the text you would like to compress. So if I were to just run this, it says, enter the text you would like to compress. That's the first thing that I see as the user. So all of these functions up here, you always put your function to the top. All of these functions are not used yet. They're just defined. They're not called yet. So it really prints out line 72. It says, enter the text you would like to compress. And then that's when the user would type in something. Okay? So if I were to type in, no way. This is what, I'll zoom in a little bit, right? This is just me. This is what I'm typing in. And if I click enter, it says, no way was the original text. It says compressing. You didn't need to type that. It just did it for like, if you're like playing a video game and it says like loading and it has like a loading bar. In a lot of cases, like that's unnecessary. It's just a way to like make it look like kind of keep you active. If you just sat there on a blank screen for a while, you'd be like, what's happening? Is the game actually working? In this case, there was really no purpose to it other than just for optics. But look, I was able to turn this into this. Now look at this. Now this didn't work because remember it said before I even started, it only worked up to 9 because 11, right? A11, there were 11 A's. 1, 2, 3, 4, 5. Yeah, 11 A's. So maybe I'll rerun this. I'll run my code. Say, all right. So N101, but then I was able to take W1A7Y, and look, the space, they even put a 1 after the space. A7Y7. So how did it do that, right? That's what's interesting to me. So I'm going to look at this. I'm going to walk through. So the user puts in what we would like to compress. We put in no way. And it printed out what the original text was with whatever you typed. Okay, and then it compresses it, and it takes no way, and it stores it as original text. Okay, we already have the original text. It saved it. Remember up here, we saved it as original text. If you highlight something in here, it will show you where else it is in the document. So if I highlight original text, it shows that I first received it when I typed in no way and stored it as a variable called original text. I'm then passing that into the compress function. So if I scroll up to find the compress function, I see that I passed in no way. No way is received as a variable called original. So every single time you see the variable original now, that is no way. All right, so we've called this function, which means we need to run it. So the result is the final result is blank because we're starting it. The current run character is blank. And the run length so far is 0. So then we have our for loop. It says for I in range, and then it has the length of original. So it's going to loop through every single character in what I passed it. And I passed it 1, 2. Let's count how many characters I passed in here. I'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 characters I passed in. Okay? And this length function, zoom in, right? This length function right here takes the, I just said 18, right? It takes the 18 and it stores it, or doesn't store it. It sets this range. It's going to go through this for loop 18 times. And it starts off and says, hey, look, if it's the very first character we're working with here, which is index 0, remember computers start counting at 0, so really be, even those 18 characters, it will go 0, 1, 2, 3, all the way up to 17. It says the current run character is whatever the original and then whatever index number we're on. So right now we're at index number 0. God bless you. We're index number 0. So it's going to take the N that I wrote in no way, and it's going to assign that current run character. And then it's going to assign the length to 1. So now we're going to move on to O. So the next iteration of the loop, O. Is I equal to 0? No, because I is now 1 because the second time through. So it runs the else. And it says the current character we're working with is now the O because it's the index 1 of original. And index 1 of original is the lowercase o in no. That's the current character. And it's saying, is that O the same as the last letter that we just went through, which is a capital N? Is lowercase o the same thing as capital N? No, it's not. So it's going to run the else, and it's going to say the run is over, right? N and O are not the same. So it's going to take n, the current run character, and it's going to put the 1 after it, which was the run length. Then we're going to reset the run back to 1. And the current run character we're going to deal with now is O instead of the previous one we went through, N. And it loops through every single letter like that. It will never hit this if again, because the if only runs if it's the very first index. If I is equal to 0, which was only the capital N. So I know this else is going to run every other time now until we're all the way done, the 18 characters in no way. Okay? And then eventually, we're going to add the result to whatever we're at right then. And the very end of everything, we're going to return the result. And that's how you would compress it. Okay, so that compression function, it's called compress. The compress function took no way and was able to turn it into this. Okay, and then if I look further down, it says decompress the text, and it runs the decompress function, and it passes what we just created, N1, O1, space 1, W7, A7, Y1. It takes that and then decompresses it. It finds the decompress function and runs that. So in looking at this, right, spend some time looking through this. And maybe you don't understand it perfectly, but at least now you've spent time looking through this problem. That's what this is meant to do, for you to look through it and for you to learn by looking through and tracing the code. If you are not tracing through the code, you're not going to do well when it comes to the create task, when it comes to the quizzes. You have to have a better understanding of this, or even just future pre-lab questions. Right? Some of you then get to the part where it's asking you to do something and write code, and you don't know what to write because you're skimming through this. Okay? Once you're done, click Save and click Next. All right. This says 886, custom image compression. If I look at the example here, I got the Spider-Man over here. Says this image is using classic RGB color representation to represent color. That's 24 bits to represent each color. Let's look at the image. Okay. Spider-Man. Now, you see, this is like a cartoon version of it. There's not a ton of bits on this screen. But what colors are being used? Shout them out. Red, blue, black, and white. So 4 colors. You're able to create this using 4 colors. And it says, look, like right now, the typical RGB color representation that we normally use, it's awesome, but it's 24 bits to represent one color, and we're only using 4 colors. It says 24 bits is nice when we want to represent millions of different colors and a very high resolution picture. But in this case, we don't need 24 bits. We want to use less. So if an image only has 4 colors, how many bits are necessary to represent 1 pixel's color? It makes you think, and you think, how many bits are necessary to represent 1 pixel's color? Come up with a custom encoding that uses fewer bits to represent each color in this image. If you were to re-encode the image using your new encoding, how many bits would you save? So it's just making you think. You're thinking, okay, key word in this, it says come up with a custom encoding. Okay, so let's break this down. What does custom mean? If I want my own custom soccer shoes, what does that mean? Yeah. You get to create them yourself, right? Get to make them. I might rely on someone else's feedback, but it means you make it up. So what it's asking you to do, it's saying you make up something. So is there a right answer? I'm asking you to customize something. If I give you a blank white t-shirt and say, customize this t-shirt, make it your own, and give you no other parameters, could you just write like a red line on the screen, a red line on the shirt and just be like, it's custom, right? You could spend hours on it, doing it, making it, but it says come up with a custom encoding that uses fewer bits to represent each color in this image. So I'm going to abide by the guidelines, but it even says in this example, it just says, hey, think about this. You're about to be asked this. So if I'm looking through this, FFF000, these are just all the bits that it's going through. So look, like, why would it include this in here if it didn't want us to play around with it, right? So if you click around, you can see all different colors. And look what's actually changing on the left, right? Look at all these possible unique colors. Do we need all of these? We only need how many? 4 colors. Okay, save, continue. Okay, I'll read through it right here. All right, the assignment. It says the image in the previous exercise used the classic RGB color representation to represent color. That's 24 bits to represent each color. However, the image only had 4 different colors in it. This all sounds familiar because we just read this, but I'm reading it again. 24 bits is nice when we want to represent millions of different colors like I just went through and showed you. But in this scenario, we only need to represent 4 colors. All right, question number 1. It says, if an image has only 4 colors, how many bits are necessary to represent 1 pixel's color? Okay, so how many bits are represent? So write your answers to each question here. So I'll say 1. How many bits to represent 1 color? I would say only 1 bit is necessary to represent 1 color. Only 1 bit. If you have 1 color, then you only need 1 bit. 2, describe a new custom encoding. We're back to this, custom. So you make up your own. I'm going to tell you mine. That uses fewer bits to represent each color in the image. Okay. So I'm going to say my custom encoding. Here's my custom encoding. 0, 0 is going to be white. 0, 1 is going to be black. 1, 0 is going to be red. And 1, 1 is going to be blue. You know what made me think of this encoding system? You know what made me think of it? Was we learned how to convert decimal to binary, right? And we have a way to represent, it starts with 1, and then we have 2, right? So if I put a 0 there, this could be 1. In binary, this is 0. In binary, this is 1. In binary, this is 2. And in binary, this is 3. So 0, 1, 2, and 3. I just added 1, see 0, 0, 0, 1, 1, 0, 1, 1. I could also make the next one, I could say it's 1, 0. If there was another color, right? Maybe I'd make it 1, 0, 0. And then I'd make the next one 1, 0, 1. And then 1, 1, 0. And then 1, 1, 1. If there were 8 colors, I would probably do it that way. But it says you're custom, which means there really isn't a right or wrong answer. But would you say this is pretty simple? Like in terms of like the custom one I just made here? All right. So the second part of the question, it says, describe a new custom encoding that uses fewer bits. Okay. So maybe I'll just say, I'll start off the question and say, I was able to create a custom encoding. They say system? What do they say? A new custom encoding. I was able to create a custom encoding by using 2 bits to represent 4 different colors. Okay, that's just what I did. You may have thought of something else. Maybe it's more complicated. Maybe it's easier. Number 3 says, if you were to re-encode this image using your new encoding, how many bits would you save when compared to the 24-bit RGB encoding? Check this out. 24 bits, 24 bits, 24 bits, 24 bits, 24 bits. So if I know that each one of these is 24, and I count all of them, it says it's 17 by 20. So 17 times 20 is 340. Okay? So 340 pixels. So I'll do the math over here. So if there's 340 pixels on the screen and each color is represented by, it says 24 possible bits, 340 times 24 is 8,160. Okay, now if that's how many bits were used, mine, okay, there's 340 pixels still in the image. So if I were to count and sit here, 1, 2, and like zoom in, 1, 2, 3, 4, 5, 6, I would sit there and count all the way to 340, right? But how many bits did I use? I used 2 bits. What's that? So 340 times 2 is 680 bits were used in my custom encoding to represent Spider-Man. So the question it's asking is, how many bits would you save? So 8160 minus 680, I saved 7,480 bits. I saved 7,480 bits using my custom encoding. So what have we learned here? We've learned that sometimes when you look at really large images and it's using the same color over and over and over again, we might be able to send it faster by compressing it. I went to go send something the other day via email and it said, this file is too large to send in an attachment. You're going to have to save it to your Google Drive and then share the Google Drive link. What was it? It wasn't even something, it was like a PDF file. Like, it wasn't even something that big. But you can compress things. Some of you may have used this with pictures or videos. You can zip files. It's a compression technique. But I saved 7,480 bits. Oh, there's a question 4. It says, if you were to decompress your image, would you lose any quality or be able to get back to the original image? If I decompressed my image, it would have lossless compression and not lose any quality. Original image would return just fine. Right? What's the reason I know that? The reason why I know that is because I didn't make any sacrifices and try to change any colors. Like, there was only 4 colors that we used. It's like, imagine there were 5 colors and one red was like slightly different. And I said, oh, that's close enough. Let's just make it red. If you realize, like, a lot of company logos, they're trying to make a lot of company logos simpler and more refined. And I can give you a separate example of that. That's not necessarily relevant right now. But the purpose of it is to make it easier to be able to edit, to be able to change the color of it, to match whatever the background is. Okay? There's different reasons why, but right here, that was 887. Okay? Any questions on that?